So as we discussed, unlike the other types of renewable energy systems that we were discussing, here we have a lot of different biofuels producing from a variety of processes. Okay, so you will come across a lot of technical terms in terms of feedstock types, production processes, products, and end use. So which is good in a sense because it is highly diverse. Okay, so for example, in wind turbine you can only generate electricity, correct? In solar PV also you can only generate electricity. Solar thermal, yes, electricity and heat. But here in biomass and bioenergy sources, you can generate a lot of products, including chemical products also. Chemical industry also can be utilizing the organic chemistry, the entire chemical industry, all the organic solvents, etc., can also use biofuels as their feedstock rather than fossil fuels. Okay, so it's a highly versatile source. It can be used for transportation oil. It can be used for oil in furnaces. It can be used as a solid substitute for coal. You can produce gas that can substitute natural gas or cooking gas. You can generate electricity out of it. You can generate heat out of it. You can use it in transportation. You can use it to generate chemically important substances. So there is a lot of variety. Okay, there is a lot of variety in the feedstock as well. So you have oil crops, as we discussed, sugar and starch crops like sugarcane, corn, etc. We have lignocellulosic biomass. This is basically the switchgrass, wood waste, etc. from forestry, agriculture, and other industries. Then biomass from waste like municipal solid waste, wet waste from agriculture, etc. Similarly, you have a set of production processes. So for example, oil crops, the primary production process is oil crops, transesterification, biodiesel. We will discuss transesterification in the next class. It's the most common process to convert oil crops into biodiesel, which can be substituted for diesel in car, like buses, trucks, etc. Then if you look at sugar and starch crops like sugarcane, corn, cereals, etc., the direct process is fermentation, which gives you bioethanol, which is a gasoline substitute. Then if you are going for lignocellulosic biomass from forestry, agriculture, and other industries like grasses, straw, sugarcane bagasse, etc., you have to use advanced biofuel processes that can degrade the lignin and the cellulose into biodiesel. And if you are looking at wood chips, etc., you can use chipping, pelletization, pyrolysis, and gasification to either produce solid biofuel pellets that can be replacing coal, or gaseous biofuels like biogas or syngas, which can be used to replace natural gas in furnaces or industries. Okay. Then you have biomass from waste like municipal solid waste, wet wastes. Here you have to do sorting and separation and anaerobic digestion that produces biogas. Okay. So then you see this whole host of products: biodiesel, bioethanol, renewable diesel, cellulosic ethanol, that is coming from the lignocellulosic biomass. Then you have wood chips, pellets. Pyrolysis will produce pyrolysis oil. Gasification will produce syngas, biosyngas it's called. Refuse derived fuel, this is biomass from waste, and then anaerobic digestion will produce biogas. Okay, so this entire host of products can be used. The first set is primarily for transportation industry like biodiesel, bioethanol, renewable diesel, cellulosic ethanol, and other advanced biofuels. These are all going into the transportation industry to replace petrol and diesel, and also kerosene in aviation engines. Okay. Then you are going for the combustion processes in furnaces, heat generation, and cogeneration. Here we are looking at pellets, pyrolysis oil, biosynthetic oil, refuse derived fuel, and biogas. All of these can also be converted into biomass derived materials and products. So in chemical industry. Okay. So that is something that can be also a useful end use for these biomass systems. So this is at a snapshot the entire energy sector of bioenergy technology, and so you see a lot of potential and flexibility here. So let's discuss a little bit on the processing technologies today also. So the processing technologies can primarily be sorted into thermochemical processes that uses heat to induce chemical reactions, biochemical processes which use biological organisms like bacteria and yeast to induce the chemical reactions. Basically, we want to have chemical reactions that convert the raw feedstock into the biofuel of your choice. And the question is, how do you induce these chemical reactions? You can induce it to heat, from heat. You can induce it through biological organisms, bacteria, yeast, etc. or agrochemical processes where you are using mechanical means or chemical reagents to induce these chemical reactions. Okay, so you have thermochemical, biochemical, agrochemical. Okay, among thermochemical, the easiest means is direct combustion for heating, cooking, and generating electrical power. So combustion of wood in furnaces and ovens, combustion of say cow dung in traditional traditional cook waves, etc. These are all examples of direct combustion way of converting the raw biomass into heating, cooking, and generating electrical power. Okay, there you don't have to do anything at all. However, in most cases you want to pre-process the system before putting it directly into heating or generation needs. One of the ways to pre-process is pyrolysis, which is an anaerobic decomposition of biofuel feedstock by using heat to produce biofuels. Okay, so you are basically heating it in the absence of oxygen. Okay, so for example, in an oxygen-free environment, if you heat your original feedstock, the heat will start to degrade the organic molecules there, and you will get a mixture of liquids and gases, and as well as char primarily. So you will get a gas fraction, a liquid fraction, and a solid fraction, which is called char. Okay, so the liquid fraction is usually called pyrolysis oil or bio oil, which can be used in thermal industries for heating and power plant needs. You can also convert wood into charcoal. So charcoal is much more energy, has higher energy content than raw wood. So that is also a way to use it. You can, so this is also often called cracking of the biofuel. This is just another term for the anaerobic decomposition. So you are basically cracking the biofuel to produce this bio oil, charcoal, and a gas component that you can also use. There are several other specific industrial processes which are also using thermochemical processes to degrade biofuel feedstocks. One is gasification. Okay, so gasification of biomass in a gasifier produces primarily what is called a synthetic gas, a mixture of carbon monoxide and hydrogen. How you do it is you have a reactor where you do a partial oxidation of your biofuel. So you give some amount of oxygen, but not enough oxygen to fully oxidize your fuel, and you get a mixture of carbon monoxide and hydrogen at the end, which is a high calorific value gas that can be used directly in the industries for electricity generation or heat generation. Okay, so this synthetic gas, a mixture of CO and H2, is the output of a gasification process. Then you also have a Fischer-Tropsch synthesis, where you can produce renewable diesel from syngas. So this syngas can be put in a Fischer-Tropsch based chemicals in thermochemical synthesis process to produce liquid biofuels like renewable diesel. Okay, so these are the various types of thermochemical processes that you can do with your feedstock to produce gases like syngas, solids like char, wood char, charcoal, etc., liquids like bio oil, pyrolysis oil, etc. Then you also have biochemical processes where you are using biological organisms like bacteria, yeast to induce the chemical reactions in the biomass feedstock. Two very important types is anaerobic digestion of biomass to produce biogas. So biogas is a mixture of methane and carbon monoxide. Syngas, remember the difference, syngas is carbon monoxide and hydrogen coming from a partial oxidation of biomass in absence of any organisms. Okay, biogas is a mixture of methane and carbon monoxide, which is used which comes through a biochemical process where you are using bacteria to anaerobically digest the biomass in again a sort of reactor. It's a significantly slower process. So a bacteria is used, anaerobic bacteria is used to digest the biomass to produce biogas, which contains methane and carbon monoxide. Okay. Both syngas and biogas can be used to replace either cooking gas or furnace gases in heating and power plant industries, but their sources and their composition are different. Okay. Another important process is fermentation, where yeast is used to convert sugars and carbohydrates into ethyl alcohol, that is ethanol biofuel. So you're using fermentation through yeast, just as you do for bread, to convert sugars and carbohydrates into ethyl alcohol based biofuels. So here you can use corn syrup, sugarcane syrup, then advanced techniques will use like the switchgrass based lignocellulosic biomass also can be fermented under advanced conditions. Okay. The third way is the agrochemical process, where using mechanical and chemical reagents to convert. Okay. So here mechanical means include pressing, crushing, filtering, fractional distillation like boiling and then condensing the condensate, etc. These are used, or chemical reagents are used. So for example, pressing, filtering and fractional distillation based separation of biofuel grade oils from oil seeds. Okay. So that is one part of the agrochemical process. Another is transesterification of this biofuel grade oil through using certain chemical reagents like methyl alcohol, and also methyl alcohol is primary reagent, which converts this biofuel grade oil into fatty acid methyl ester based biodiesel fuel. We will discuss this a little bit more detail later. Basically, most biodiesels is a form of methyl esters, which is called fatty acid methyl esters, and this is done through this transesterification process, where you are combining methyl alcohol with these biofuel grade oils to produce this biodiesel fuel. Okay. So if you look at that entire research loop here, what are the main areas that you need to work on if you want to do research in biofuel technologies? You have to work on sustainability, like produce biomass for biofuels and bioproducts with minimal to positive impacts of environment. So you can do research in the feedstock growth and management. You can do research on how to increase the production rates of algae, genetically engineered algae, etc. Then you so the overall sustainability of the entire biofuel production chain. Okay. Then there is also importance of developing improved plant biomass. So develop crops with cell walls optimized for deconstruction and conversion to biofuels and bioproducts. So you can produce genetically engineered crops or specifically grown strains of crops where the lignin and the cellulose components are easily degraded and converted into sugars and vegetable oils, right? So this is more of a plant technology or agricultural technological aspects. Then you have chemistry aspects, developing better enzymes and microbes that break down the biomass into sugars and lignin. So this is more crop technology, this is more biochemistry. You are improving the enzymes and the microbes to break down the biomass into sugars and lignin. And finally, the chemical conversion, like engineering metabolic pathways in the microbes to produce biofuels and bioproducts, and improving the chemical reagents as well. So all of these are important research areas where current research is going on. So given all of this, what is the current status of sustainability of the biofuels that we have today? Okay. So this is an estimate. So this is again this part, the sustainability aspect. People do measurements of the sustainability of the biofuels. We will discuss later in this course how to do a life cycle assessment as well to some extent. So here we are looking at three cases where biofuel is used to generate only electricity, where biofuel is used to generate heat, and where biofuel is used to generate electricity and heat. So a cogeneration process. Okay. And this is grams of CO2 equivalent per megajoule. So how much CO2 is emitted per megajoule of electricity or thermal energy produced. So for electricity, the mean is around 40 grams of CO2 equivalent per megajoule for current biofuel systems, life cycle CO2 emissions. And the variability is quite large. You can go up to 200 and go down to 0. So you have to be careful of which system you are using so that you are not actually emitting more than your fossil fuel systems. Okay. So that is one issue. Then you have for heat, the process is much easier. So you are generating much less CO2, 0 to 10 grams per megajoule. And when you are doing a cogeneration system, you are actually sequestering a lot of CO2. So you have a negative emission imprint of around minus 30, minus 40 grams of CO2 per megajoules. Okay. So clearly, cogeneration, we are using your biofuels to generate both heat, which is used in the industries, and electricity is the best. Generation of heat itself is the next best, and electricity will have significant emissions associated with it as far as current practices stand. Okay. Similar situation with life cycle SO2 emissions. SO2 is a pollutant. You have a large emissions when you are generating electricity, smaller emissions where you're generating heat or electricity and heat together. Okay. This plot here shows the CO2 emissions from all types of utilizations club, but differentiated in terms of the feedstock that is being used. So this is first generation biofuels with impact of land use change also integrated. Remember, first generation biofuels are competing with your agricultural resources and it needs fertilizers, insecticides and all of those things. So if you convert a arable land area for biofuel production, the food that was to be grown there has to be converted somewhere else. So extra land has to come under agriculture, okay, to avoid constraints in the food production. So land use change becomes an important criteria, because if you are converting forest land or grasslands into agriculture, it emits CO2, okay, apart from the ecological problems that creates. Okay. So you see here, this red line at 100 is the fossil fuel reference. So fossil fuel basis around 80 to 90 grams of CO2 per megajoule. Okay, so that's the fossil fuel reference. Okay, you can also use this reference here also as a reference. Now, if you see for certain types of biofuel feedstocks, including molasses, palm oil, rapeseed oil, soybean oil, and sunflower oil, the mean or the median emissions. So the mean is given here, and this black line is the median. Okay, mean and median are somewhat different, but all of them in general have larger emission footprint than fossil fuels. Okay, so clearly, if you consider land use change as well, these types of vegetable oil to biodiesel conversion systems where using crop-based plants is not sustainable. It's worse for the environment. However, if you look at the other cases, sugarcane from bioethanol, sugar beet-based bioethanol, then corn-based bioethanol also to some extent, here you have emission profiles which are lower than the fossil fuel-based systems. So it's around 60% to 50% of the total emissions if you look at the mean case. Okay, the median case is somewhere here. Okay, so around 50%. So here you can see that bioethanol production, even first generation bioethanol production, does produce significant savings in CO2 emissions. So bioethanol in general is useful, not as much as you want, but sufficient for you to consider it as a sustainable practice. Okay. Now if you switch to second generation biofuels, okay, so here land use change is incorporated, but the land use impact is much lower. And here you have sugarcane bagasse, corn stover, straw or husk from wheat production, switchgrass, miscanthus, forest residue, short rotation coppice. These are all second generation biofuels, either grass-based biofuels which are not competing with arable land, or agricultural or forestry waste. Okay. So here the emission profiles are all ranging from, if you look at the mean and the medians, around 10% to a maximum 40%, 40 to 50% of the fossil fuel based emission systems. So what you can see here then is that you are getting much better sustainability for these when you are considering life cycle CO2 emissions. Okay. So this kind of gives you the rationale for moving from first generation to second generation biofuels. Okay, so we will stop here today. In the next class, which will be the final class for biofuel technology, we will discuss a little bit on the various types of biofuels, biodiesel, bioethanol, etc., and a little bit on how the processing like transesterification, fermentation, etc. work. Okay. Thank you for listening, and we will meet again in the next class.